So in the last class we looked at the upcrossing probabilities. It's an estimate on the expected number of times we go up in a martingale, in a sub-martingale. And in this class we're going to make a very beautiful application of this. It's the martingale convergence theorem. So there are several theorems involving the convergence of martingales. This is perhaps the simplest one to apply. And I'm going to jump straight to the statement. So theorem. Sorry. So it's a beautiful statement, a very simple one. Suppose that xn is a sub-martingale. So here, what we are assuming implicitly is that there exists a filtration. Xn is adapted to that filtration. All the xn's are in L1 and satisfy the sub-martingale inequality. And we also assume that the supremum over n of the expectation of xn positive part is finite. So somehow, although a sub-martingale is something that's supposed to grow, somehow it's not growing too much. So in expectation, x plus is uniformly bounded in n. And what statement of the theorem gives us is that xn will converge almost surely to some x, and moreover, the expectation of the absolute value of x is finite, or in other words, the limit is in L1. So this is the main theorem of this lecture, and it's not going to be very hard to prove. We're going to make strong use of the upcrossing estimates we did in the last class. So here's the proof. Okay, before jumping into the proof, I would like to emphasize the importance of this statement, because verifying that something is a martingale or a sub-martingale is not especially hard. I mean, depends on the process, of course, but as soon as it is, it's a bound on conditional expectations to prove that something is a sub-martingale. And expectations are easier to deal with than, for example, trying to get estimates on weird events like the ones that appear when we look at convergence, right? So if you're trying to show that something converges, we need to show that we first need a candidate, then for every epsilon, there exists an n0. So these are complicated events, while proving that something is a sub-martingale only involves calculating expectations and conditional expectations. So this is the good part. And this convergence is a bit surprising at first. When we look at the applications of this theorem, they're all gonna surprise a little bit that this convergence even takes place. So let's just jump into the proof. We already have, for every a smaller than b in R, an estimate on the number of times that our process goes from below a to above b until time n. So just to illustrate again what this event is about, we have here our sub-martingale, and we have some thresholds b and a and b, and the number of upcrossings is just the number of times we go like this. You see, we go from a point below to a point above, then again from a point below to a point above. So here, if this is the value of n, the number of upcrossings here is 2. So we already have an estimate on the expectation of UAB n, which is given by the upcrossing theorem, bounding this by the expectation of xn minus a plus minus the expectation of x0 minus a plus over b minus a. So let us massage a little bit this right hand side. So the expectation, the first expectation there, can be bounded by the expectation of xn plus the absolute value of a. So no matter if a is positive or negative, we can always use the triangle inequality to get the positive part on xn, and then a will get the worst possible sign here. Here we still have b minus a, but the right hand side is the expectation of a positive random variable. So we can just drop this negative term and upper bound the upcrossing probability expectation by this. Okay, so another interesting observation is that the upcrossing from a to b until time n can only grow as n goes to infinity, right? If we take a larger n, if we had 3 upcrossings, after we increase n, maybe we have 4 upcrossings, 5 upcrossings, but no less than 3. So this is a family of random variables that are growing with n to some limiting random variable that of course could take value infinity, right? So could be that we have infinitely many crossings from A to B. But now let's look back here. If these random variables are growing towards this random variable, then their expectations are going to be bounded, are going to converge to the expectation of this by the monotone convergence theorem. So it means that the expectation of UAB, the final number of upcrossings, is also bounded by the same random, the supremum over n of the expectation of UAB n, which is bounded by, let's look here, the supremum over n of the expectation of xn plus the absolute value of a over b minus a. So I'm just taking the supremum on the above inequalities. Now the interesting fact is that according to the statement of the theorem, this supremum is bounded. So all of this is finite, because we're taking something finite, summing constant, and dividing by another constant. So in particular, it means that UAB is finite almost surely. Let's see where this brings us. So we are going to the next page. So we have a graph here, and we fix lines B and A, and we know that the number of times that our process goes up is finite, even when we look at infinity, at time going to infinity. So let us look at what this implies when we consider infinitely many different A's and B's. So I'm going to look at A's and B's that are of course rational, because I don't want to take an uncountable number of pairs in this union, and such that A is smaller than B. And what I want to look at is the fact that U, A, B is finite. Sorry. the intersection. Okay, this is an event that has probability 1. Why? Because this event we just saw has probability 1. Almost surely UAB is finite. So here we are intersecting a countable family of events of probability 1. So the probability of this intersection is 1. So what I'm saying is now, no matter what pair of lines you take here, you only cross finitely many times. Why is this interesting? Because if the lim inf over n of xn is strictly smaller than a, strictly smaller than b, strictly smaller than the lim sup in n of xn, then the upcrossings from a to b are going to be infinite. If we go below a infinitely many times and we go above b infinitely many times, then the number of upcrossings has to be infinite. In particular, with probability 1, we have that for all a's and b's rationals with a smaller than b, the lim inf of xn, no, now I want to negate, it's going to be easier to write the, so with probability 0, there will be no pair of points such that the lim inf is smaller than a, smaller than b, smaller than the lim sup. And if this doesn't happen, then we almost have a proof that xn converges. Okay, so what we know up to this point is that there is no oscillation in the process x. So if x is oscillating, then we can find rationals like this and this. Oh, sorry. So that the upcrossing is infinite. So if you remember, any sequence, this is a result of real analysis, any sequence xn has one of the three possible behaviors. Either the limit is infinite, or it's minus infinite, or it oscillates. Okay, so this we already know does not happen, because if it oscillates, we can find two rationals between which it will upcross infinitely many times. So we are left with these two possibilities. Okay? Now let's look at the so what we know is that the lim inf of xn and the lim sup of xn have to be the same. So in these two cases, the lim inf of xn is equal to the lim sup of xn, and we define this to be x. Now x could be infinity, or x could be minus infinity. We don't know that yet, but at least we can define the limit. Okay, so now we are going to show that x is finite, and we do this by looking at its expectation. Why? Because we know that we have a bound, a uniform bound on the expectation of this. So we first look at the positive part. Okay, we know that this is the lim inf of this. So by Fatou's lemma, this expectation of a lim inf is smaller or equal than the lim inf of the expectations. which is smaller or equal than the supremum of the expectations, which by hypothesis is finite. So in particular, this is finite almost surely. So this we can rule out as well. Now this was easy because this is exactly the part that appears in our hypothesis, right? It's the part that involves the expectation of xn plus. How are we going to deal with the expectation of x minus? So this is just a trick. The expectation of x minus is the expectation of x plus minus the expectation of x. This is always true. Actually, even without the expectations. Any number minus the negative part of a number is always the positive part of the number minus the number. So we do this with the n's here. And let's recall that this is a sub-martingale. So what happens with a sub-martingale is that the expectation is always growing. So this is bigger than the expectation of x0. With a minus sign, this is smaller than x0. And this term, we keep it intact. Now, we know that the supremum over n is smaller or equal than the supremum over n here, which is also finite by hypothesis. So we managed to bring something concerning x minus into something concerning x plus, and something that does not depend on n, so we can take the supremum and still get something positive. Sorry, something finite. So in particular, again, this is finite almost surely. And let's go back. We just proved that this case is also impossible. We cannot have x be equal to minus infinity with positive probability. Good. So there's still something left. Let's go back to the theorem and see what we have proved up to now. So we've proved that under this hypothesis here, there exists something that is the almost sure limit of xn. And moreover, we proved that the expectation of x plus and the expectation of x minus is finite. So we also proved, if we look here, that this expectation is finite, this expectation is finite. So finally we get that the expectation of x in absolute value is finite. So x is in L1. So this finished the proof of the theorem. And in the next class, we're going to look at other results about convergence of martingales. But this is perhaps the cleanest result we have. But now, before we move on, we're going to see an application of this result. And the application of this result is going to be about the recurrence of random walks. So now let's take another page here. So applications. The recurrence of a random walk. So first let's explain what I mean by this. So let's take psi I, an IID sequence with distribution delta of 1 plus delta of minus 1 over 2. Sorry, this is 2, this is 1. So what we're doing here is tossing a coin, a fair coin, and jumping up or down with probability 1/2. And we define xn to be the sum for I from 0 to n of psi I. So this is a simple random walk. And let's actually sum one here. So it's a simple random walk starting at 1. By the way, I'm gonna make a small change here. I'm gonna start this sum at 1 so that at time 1 this sum is not playing any role and you just have a 1 here. And at time 0 we start at 1, and at time 1 we already start to sum. So if we plot this, this is going to start at 1 and jump up and down. Okay, so this is a martingale, right? We saw this when we saw the introduction to martingales. So X is a martingale. In particular, X is a sub-martingale. Okay, so it's a martingale, it's a sub-martingale, and a super-martingale. Okay, now what we do is we're gonna define a stopping time t, which is the first time in which the first time for which xn is 0. Okay, so in this particular case of the graph I plotted here, this would be the time t. It's the first time the random walk hits 0. And what we're going to show now is that t is finite almost surely. So with probability 1, we're going to hit 0 in a finite time. This is what we call the recurrence of the random walk. Okay, how are we going to prove this? So first, we don't care about what happens after we hit 0, right? We are only looking at what happens until this time. So what happens after doesn't matter to us. Let us forget this, what the random walk does after t. How can we forget what the random walk does after time t in a rigorous way? So we define h, a predictable process. It's going to be t strictly smaller than, the indicator function, that t is strictly smaller than n. So what does this process do? It's 1 up to here. I made a small mistake here. It's the opposite. It's t bigger or equal than n. Is this correct now? So it's 1 until time t, and then it's 0. Okay, let's see if this is predictable. Okay, so what we have to show is that simply this event, t bigger or equal to n, belongs to fn minus 1. Okay? So why is this expected? So again, we did a similar calculation in the last class. The complement of this event is exactly t strictly smaller than n, which is t smaller or equal than n minus 1, which belongs to fn minus 1, because t is a stopping time. Okay, so we know that h is predictable, and we look at what hx is as a process. This is a process that's going to follow x until time t, because until time t we are using h equals 1, and after that time we are going to just stick to 0. So maybe the process x continued to do something, we don't care, we stay at 0. So this is the first step of the proof. We forget what happens after time t. Now another thing that we do is important here. If we consider this new process y, this new process, we would like to use the sub-Martingale convergence theorem, but there is a problem. So y is a martingale. Great. It is in particular a sub-Martingale, and it could in principle use the Martingale convergence theorem, but when we look at the expectation of yn plus, we don't know how to estimate this. So this could grow to infinity, this could be unbounded. So we don't know how to deal with this. So what we're going to do is define Zn to be minus yn. So just reflecting everything here. And the advantage of doing this is that x is going to be again a martingale, right? Sorry, Zn is a martingale. And Zn is going to be smaller or equal than 0, almost surely. So in particular, the expectation of Zn plus is equal to 0, which is uniformly bounded. So the supremum over this, over n, of the expectation of the positive part of Zn is 0. So Zn is also a sub-martingale with uniformly bounded expectation of the positive part. Therefore, by the theorem we saw before, the sub-Martingale convergence theorem, Zn plus converges almost surely to some Zn plus no, Zn converge to Z. And this variable is finite almost surely. In particular, right? If it's in L1, it's finite almost surely. Now let's look at an interesting fact about Zn, right? Zn has two very different behaviors. So let's look at what happens between time n and time n plus 1. So this thing here is always bounded by 1, right? We are jumping jumps of size 1 or minus 1, and sometimes we are stopping. When we hit t, we stop. So that difference is going to be 0. But let's be a bit more precise. This thing here is equal to 1 if n is smaller than t. And it's going to be 0 if n is larger or equal to t. So let's look here again in the graph. So until we hit time t, this is going to be 1. Absolute value of minus 1 is also 1, 1, 1, 1, 1, and so on and so forth until we hit n. From now on, it stays, and this difference is always 0. So on the event that t is equal to infinity, meaning we never hit the origin, we have Zn minus 1, n plus 1, minus Zn is equal to 1 for every n. So this is strange because we know that these random variables are converging. In particular, Zn is not Cauchy, and Zn does not converge. So this has to have probability 0. Because we know that Zn converges almost surely. So let's recapitulate. We want to show that this random walk here hits 0 with probability 1. So we want to show, the way we are going to show that it hits 0 is by using the Martingale convergence theorem to show that it converges. Something that is jumping all the time and we kill it once it hits 0, so it makes this modification here to kill it once it hits 0. If it converges, it's because it hit 0, right? Until it hits 0, it's oscillating, it cannot be converging. So if it converges, it's because t is finite. Okay, but we don't know how to estimate the expectation of y, positive part. So we go to z. Z is bounded by 0. So we know how to estimate this expectation. And we get it. We get the convergence of Zn, and in particular, t is finite almost surely. So this finishes the class, and let's resume with other convergence theorems for martingales in the next class. Thank you.